Okay, let's do a little bit more from section 3.2, just another example here. This is page, where are we at? Page 10, right? Oh yeah, page 10 of the chapter 3 notes. Another one of these two-way tables. We have two categories, major, nursing or non-nursing, and sex, male or female. Okay, so here we go. Find the probability that a randomly selected student is, and then you have some different questions. What's the probability that a student is a nursing major? So starting off with the simple ones. Okay, so there are a total of 3,537 students in the study. How many of them are nursing majors? So it looks like right there, right? Nursing major total, 795. So calculator help, 795 divided by 3537. It says to round to 3 decimals here, so that's going to be a 225. 0.225. What's the probability that the student is female? So we're still going with that same total, 3537. Just need the female total, 2427. Round to 3 decimals. I'm getting a 0.686. We're all warmed up. Okay, we got those. As long as I didn't make any typos, I should be good. Okay, here's one of those that's a given that. So that's a conditional probability. Right? A nursing major given that the student is female. So as soon as you see that given that statement, go find the total for that description, which is female. And I need that total female 2427. That is going to be your denominator. Okay. And then of those 2427, how many of them are a nursing major? So stay within that row, and it's 700. Calculator, your turn. 700 divided by 2427. And we got 0.288. All right, let's circle my answers. Okay, good so far. Now here's a new type, nursing major and female. I know we've already said that and transferred or translates to multiplication. True, except for when you have a table like this, there's a quicker way. So I would suggest not doing the multiplication formula. Just find the numbers is the strategy. Just find the numbers. Okay, here there's no condition. So I know the denominator is going to be that grand total of 3537 because there was no given that or any condition on the person being selected. Therefore, now I just need to go find the total number of people that are both nursing major and female. So is there anybody that's female and a nursing major? Okay, so I can look to female, nursing major. What corresponds to both of those is that 700. Right? There are 700 students that are both a nursing major and female. That's the number I want. Do the calculation, and you should be good to go. It looks like a 0.198 on my calculator. All right. Finally, are the events being a female student and being a nursing major independent or dependent? To answer this question, I would look at the questions A and compare it to C. Because check this out. The probability that we randomly select a student and they are nursing major is that, right? About 22%. If we put a condition that the student is female, the probability of being a nursing major goes up to about 29%. So the condition being female changes the probability of being a nursing major. Now, is this significant enough to warrant a significant change? I mean, 22 up to 29. Okay, we'll say yes for now. We'll get to that later. But for now, we're going to look at that and say, yeah, I would say these are dependent, because the fact that we know the student is female changes the probability that they will be a nursing major, right? So had these two been the same, then it doesn't matter if the student is female or not. The probability of being a nursing major doesn't change. But here, that condition of being female changes the probability. Therefore, they are dependent events. So I'm just going to write dependent. I just explained it in words. All right, we've got one more example for this section. A research shows that approximately 1 woman in 700 carries a particular gene, a mutation of a particular gene, and about 71% of women with this mutation develop skin cancer. Okay, find the probability that a randomly selected woman will carry the mutation and will develop skin cancer. So, and typically translates into multiply. And our first probability is, what's the probability that a woman carries the mutation of the gene? That's that 1 in 700, right? So I'm going to do 1 over 700 times, because it's and then given that the woman carries the mutation, what's the probability that they develop skin cancer? That's that 71%. So I'm just going to write that as 0.71. Right? Let's do 0.71 to not be too confusing here. And so in my calculator, I'm doing 1 divided by 700 and then multiply that by 0.71. So 1 divided by 700 and then times that by 0.71. I'm saying about a 0.001. My final answer. Okay, we're well on our way. There's 3.2. Give the homework a try. If you have any questions, feel free to email or call me, and I'll respond as soon as I possibly can. Hope all's well. Talk to you later.